All right, today we're going to talk about work and what work is. And obviously, it's going to be a little different than the work that maybe you're thinking of. So there are three things that have to happen for work to happen. One, there has to be force being applied. Two, there has to be displacement. So the object has to move that we're applying the force to. And then there has to be cause. So in order for a force to qualify as having done work on an object, there must be displacement, and the force must cause the displacement. So that's what it means. So let's give a couple of examples. A teacher applies a force to a wall and becomes exhausted. Okay, applying a force, yes. Is the wall being displaced? And the answer is no. So therefore, we're doing no work. A book falls off a table and free falls to the ground. Okay, so is there a force acting on the book? And the answer is yes, it's gravity. Is there displacement? And the answer is yes, it's falling to the ground. And does gravity cause that? Yes. So there is work being done. A waiter carries a tray full of meals above his head by one arm straight across the room at constant speed. Work or no? This one requires a little more thinking. So if we're holding it above our head, all right, so the force is going upward. We're displacing, but we're displacing to the side. So is the upward force causing this displacement to occur? And the answer is no. It's no work being done by the waiter. Okay, the waiter is holding it, or I mean by the lifting up, right? Lifting up does not cause the work to be done. It's the waiter walking. All right. So the big thing is the force and displacement need to go in same direction, or at least can't be perpendicular to each other. A rocket accelerates through space. Work or no work? Well, there has to be a force for it to accelerate. Is it displacement? Yes. Is the force causing the displacement? Answer is yes. So the answer is yes. There's work occurring when a rocket accelerates through space. So there's some examples and things to think about. Now, the formula for work is right here. Force times distance times cosine of theta, okay? Theta is just the angle between the force and its displacement. And there's some examples that we'll do on the board. It's trying to find that angle. So here's some different examples. Here's the first example. The force is going right as it's displaced to the right. So force and displacement go the same direction, which means our angle is going to be 0 degrees. So then we'd find the cosine of 0. Hint, cosine of 0 is 1. So really work is force times distance, or displacement when we talk about this. In scenario B, we're going this way with our displacement, but our force is going opposite, all right? That leads us to 180 degrees. The cosine of 180 degrees is -1. So we'd still take d times f, but it'll be times -1. So it'll be negative work in this case. And then the one we just talked about with the waiter carrying the tray, we got force going upward, displacement going that way, so our angle is 90 degrees. If this happens, the cosine of 90 is 0. So we're taking d times f times 0, which means our work will be 0. So to rehash, if they're going exactly in the same direction, it's force times displacement times 1. If the displacement and force are complete opposite directions, it's force times displacement times -1. And then if they're at 90 degrees, it's force times displacement times 0, which means our work is 0. Whenever f and d are in the same direction, theta is 0 degrees. So even if we're pulling, say we had a string attached to this cart and we're pulling it up. As we go up, since they're on the same plane or in the same direction, our angle's still 0 degrees, even if we have an angle to our ramp. And we'll do something that kind of plays with that later on. So what does negative work is? Well, the force doesn't cause the displacement, but rather hinders it, all right? And that's called negative work. The negative work refers to the numerical value that results when f, d, and theta are substituted into the work equation. So that means it's just, it doesn't cause a displacement, but rather stops it from being displaced. That's what negative work does. Okay, units of work, we use joules to describe work, not the joules that you smoke with, but a joule that is work. A joule is a Newton meter, all right? So 1 joule is N times M. Other standard unit or non-standard units of work, foot times pounds, right? So it's going to be a distance times a weight. Kilograms times meters per second squared times meters. which is the same as this, kilograms times meters squared per second squared. But all of these could be considered units of work. So let's talk about work in this case. So we have a 100 Newton force applied to a 15 kilogram object, a horizontal distance of 5 meters at a constant speed. So it's going in this direction for 5 meters. Force and displacement are going in the same direction. So our theta is 0. So I take 100 times 5 times the cosine of 0, which is 1. So it's 100 times 5, 500 joules of work being done here. Diagram B. So we're applying this force. We're like at an angle to the direction it's going. So it's moving 5 meters this way, but we're going at an angle. So we would take 100 times 5. I'm doing this in a calculator. That's supposed to take me some time. Times the cosine of 30. That's when you would use 30, or the angle that you're given. And I get 433 joules of work being done. And then this last one, we're lifting something upward 15 kilograms to the height of 5 meters at a constant speed. If it's going at a constant speed, the force is going to be the same as weight. So weight is gravity. So 15 times 9.8 is the force of gravity, which is 147. So our force is 147. And since we're lifting up at 5 meters, they're both on the same direction. So our cosine is 0, so it's 1. Cosine of 0 is 1. So I take 147 times 5. And I'm doing 735 joules of work to lift that object up. Here's a problem we're going to do on the board. A 10 Newton force is applied to push a block across a friction-free surface for a displacement of 5 meters to the right. Do it now. All right, so we have this diagram. We have a 10 Newton force applying to push a block across a friction-free surface for a displacement of 5 meters to the right. So our displacement is going 5 meters this way, okay? So these two forces here, all right, we could find the work being done, but if the displacement's going this way and you're going up or down, we're at 90 degrees. Now, if you get your calculator and hit cosine of 90, that's 0. So this one and this one are doing no work. Now, with this one, right, work, force times distance times the cosine of theta. Force is 10 newtons, distance is 5. And since they're both on a flat plane, right, our angle is 0. Cosine of 0, again, put it in your calculator to check me, is 1. So 10 times 5 times 1, 50 joules of positive work, because we're going in the same direction. A 10 Newton force is applied to push a block across a frictional surface at constant speed for a displacement of 5 meters to the right. Only thing that's different is there's friction. Do it now. All right, so similar to our last problem, we got 10 this way, but now we have some friction going along, and we're still going, make sure it's the same distance. Our displacement is still 5 meters this way. So again, these two do no work because they're at a 90-degree angle, which means our cosine of 90 is 0, so no work. This one would be our force 10, so work is force times our displacement of 5 times our angle cosine of 0, which is 1. 50 newtons. Now, I'm going to talk about this one. So now our displacement's this way, but our force is going that way. So when I look at that, I look at this angle, and it's kind of like an angle where it's going this way, all right? So it's going to be 180 degrees. Now, how that applies, I'm getting a calculator out just so I can type it in as I tell you, is that if I take the cosine of 180 degrees, okay, so it's going to be this. It's going to be work is force, which is 10 newtons, times our displacement of 5, times the cosine of 180. The cosine of 180 is -1. So knowing that, it's 10 times 5 times -1, -50, that should be joules, right? So I'm doing 50 joules of work pushing it this way. Friction's doing a -50 joules of work, my net energy is going to be 0, okay? Even though we're still moving, our net work is going to be 0 in this case. An approximately 2 kilogram object is pulled upward at constant speed by a 20 Newton force for a vertical displacement of 5 meters. Do it now. All right, so we're pulling something upward. We're pulling something with a 20 Newton force for 5 meters. The other thing is that when we're pulling something up, there's another force, and it's the force of gravity. Our force of gravity is going to be 2 times g, which this is approximately 2, so we're going to use approximate for g. We're going to use 10. So 2 times 10 would be approximately 20 newtons. So now we have a 20 Newton force going up, gravity's pulling down 20 newtons, and we want to talk about work. So since this is going in that direction, right, these two are at an angle of 0 degrees, so work is force times displacement times the cosine of 0. Sorry, cosine of 0. That's 100 joules of work. Now, our displacement's going this way. It's 180 degrees to our force, right? It's in the opposite direction. So work is going to be 20 newtons times 5 times the cosine of 180, which is negative 1, which gives me negative 100 joules of work. So we're doing 100 joules of work to lift it. Gravity's doing a negative 100 joules of work holding it down. It evens out at the end, and our net work is going to be 0. And a force of 50 newtons acts on the block at the angle shown in the diagram. The block moves a horizontal distance of 3 meters. How much work is done by the applied force? Do it now. All right, so we're doing 50 newtons force at a 30-degree angle to the surface, right? We're on a surface here. No friction, so don't worry about that. But we're pulling at a distance of 3 meters this way, all right? So now when we pull something at an angle like that, and as we pull up, part of what we're pulling is out, right? We're pulling out towards us, but there's also part pulling up. But the only part that does work is the part that's pulling out, because that's the same direction as this. So we have to figure out what that is. And it's built into the equation, so you don't have to do any kind of fancy math, because work is force times distance times the cosine of our angle. So our force is 50 newtons, right there, right? Our displacement's 3, and then cosine, since we're at an angle here, is 30. So, again, I'm going to do this on the calculator. I'm going to take 50 times 3 times the cosine of 30. And you can see the answer here. I'm going to round it. I'll go 2 sig figs and just say 130 joules of work. But I'm only doing 130 joules of positive work here, all right? If I was just pushing it, so let's say I'm doing this instead, and I just want to give you a comparison. If I'm doing this instead, and I'm pushing 50 along, right? My angle is going to be not 30, but 0, so it'd be 5 times 3. So if I'm just doing this, I'm doing 150 joules of work to make it go that same 3 meters. So by pulling at an angle with the same force, I'm actually doing less work to get the same result. Something to think about.